with this. And maybe if we have another volunteer, maybe we can take a look to another sample.
Before we see another sample, Abdon,
Yes.
would you please, if that's in your area at all, some people talk about nanotechnology
Yes.
in doing the flash drives that everybody of us use, or computers even. So how do you see the nanotechnology practices or approaches doing the wafers that are used, something?
Yes.
So can we just have an application that everybody can relate to?
Yeah, definitely, definitely. One of the, and this is actually pretty related because in here in our lab at CNU, we do nanocharacterization, but we do also nanofabrication, right? So one of the biggest applications that kind of triggered all these, all these, especially investment from industry, is of course fabricating transistors.
Yes.
Right?
Yes.
So pretty much what happened with that is if you can decrease the size of a transistor and increase the efficiency, you can have you can have smaller computers and faster computers.
Yes.
Right?
Yes.
So the keys to that are not only the just making them small, but also the synthesis synthesis aspect, or let's say nanofabrication aspects, right?
Yes.
So for this, there is I do not have actually I do not have any sample loaded right now, but we have some transistors and some other materials from to actually show in the remote access that is not loaded right now, but I can quickly go over it. Basically, in a nanofabrication process, for example, in lithography, right?
Yes.
You take a semiconductor such as silicon.
Yes.
And you can, through several processes of, masking and etching, you can design and fabricate your devices. Mostly a transistor, for example.
Yes.
And in order to do that, you need the tools to characterize that and to fabricate that.
Yes.
So in here, in Penn State, we're running here both in parallel. So we're using actually this FESEM a lot to see what the students in our program, they're fabricating their like devices from lithography processes in silicon. And these tools are absolutely essential to not only fabricate, but to control and measure exactly the performance of these transistors.
Very good.
So this is, we have what I can quickly go. It's not a transistor, but we have loaded right now. I think it's
a CD or DVD or something.
We don't have it right now. I kept the samples the same as the previous class.
Okay.
So they had the same.
Okay.
The same
opportunity.
Samples,
yes.
Right?
Yes.
But for example, CD and DVDs is a good example on how this nanotechnology helps, and affects daily life technologies, right?
Yes.
For example, I personally, I'm a big fan of vinyl music.
Okay.
So I still have my vinyl records in here with the turntable. And they have some size and some, they have, you can encode in those ridges so much information, right?
Yes.
But with different, the the advancing technologies, if you're changing your wavelength, instead of being mechanically, for example, a CD or a DVD or a Blu-ray, what you have is a smaller etchings and higher resolution for reading these memory systems, right?
Yes.
So from a CD, DVD, and Blu-ray, these smaller etching tools allow you for to put more information in a smaller device.
Yes.
Right?
Yes.
And for example, I think it made it the news this week that I mean, someone did it previously, but I think they put a full movie encoded on some strand of DNA, right?
Yeah.
That's like the extreme.
Yes.
If you go really that small, you can encode all kinds of information.
Yes.
So this is one of the really applications for that.
Thank you.
Sure, you're very welcome.
Now let us have one more sample of your choice, and then
Okay.
we'll open it for some discussion and questions.
Definitely.
So
Definitely.
pick up one for us, and we will
Okay.
have one volunteer here. Any volunteer?
Okay, so I think what it could be interesting, this is one sample that we didn't look at.
We have a volunteer. We have a volunteer, Martina.
Okay, great. What's your name?
She will come here and tell you her name.
Hello, my name is Martina.
Hi, Martina. How's it going?
Good, how are you?
Let's see so I'm correcting for the stigmatism aberration right now. Sometimes it's easier than other times. Okay. All right. This looks good. We can see we can actually measure this thing. So these fibers, they're around 124 nanometer. This is pretty small. And what happens is the more fibers that you have, and the more surface area that you have, right? So you're having the smaller your fibers are, the better coverage of all the surface that you have. And with this hierarchical surface roughness, with the micro size posts and these nanofibers, the plant is very effective on keep pushing out the water of its surface. So in reality, the leaf never really gets wet from the water from rain, for example. And this kind of design in a lot of these plants has inspired all the surface engineering for the past 15-20 years for making super hydrophobic surfaces for microfluidics, for medical devices, for cell adhesion, all these really high super hydrophobic surfaces. They're all inspired by this plant. This is how I started actually doing research for one of project related to this a while ago. Yeah. Does it make sense?
Yes.
Yeah. Do you have any questions?
Yeah, Mr. Pena.
Yeah.
I have one question. These particles are made by fiber or protein, or what is this actually?
This is a wax actually. This is some kind of wax that is it's hydrophobic by itself. It doesn't let absorb water, but the roughness, it enhances the hydrophobicity a lot. For example, take for example Teflon, right? The Teflon is on your these anti-adherent cooking pans, right? It's very hydrophobic, but flat Teflon can give you, it's the hydrophobicity is limited. It has like an upper boundary of that. But if you could increase the roughness and get like a nanofiber system like this for Teflon, then you will have a completely super hydrophobic surface. So in this case, is a similar idea, but with wax that the leaf secretes on the outside. So this wax is with this roughness is keeping all the water away from that. Does that make sense?
Thank you.